So welcome back. So we have started already with the module number 4, which is microwave semiconductor devices, right? So again I'll just revise it. So we'll take only one topic today, which is parametric amplifiers. Okay. So as I discussed yesterday also, the first and second World War in 1945 and 1948 respectively led to the discovery of many new devices like lystrons, magnetrons, and traveling wave tubes, which are abbreviated as TWTs. So why this were required? Because obviously aeroplanes were flying a lot here and there, so there was a tendency, not a tendency, there was a requirement to transmit signals from the ground to the aeroplane, right? So and one of the most important thing was to detect an enemy aircraft in our location, right? So for that radars were very important. So somehow or the other, the microwave tubes come into picture for these applications. So that is why these tubes were discovered. So even though we say world wars caused a havoc in the world, so there are some side effects which are good also for this. So that is what I want to underline here. But what is the problem with these microwave tubes where they are very heavy and bulky? So we required a replacement for them. So these replacements are microwave semiconductor devices, right? So they are used for wide number of applications, right? Detection, mixing, frequency, multiplication, phase shifting, attenuation, switching, limiting, etc. Right? And so they are what microwave semiconductor devices also called as solid state devices, right? So the first device which we saw is varactor diode. Right? So what is a varactor diode is? It is essentially a variable reactor diode or a voltage variable capacitance for a reverse bias PN junction only, not a forward bias. It does not work at all in forward bias. So as you see in this diagram, so you have a PN junction diode separated by a depletion region of width W. So P is connected to the negative terminal and N to the positive terminal. So it is a reverse bias device. So what happens if there is a zero bias, that if there is a short circuit, a maximum capacitance is achieved. But if you increase the reverse bias, that is you increase the negative voltage, what will happen? The capacitance will decrease, right? So the capacitance is maximum for zero bias and varies inversely with applied reverse bias voltage, right? So what will happen as you increase the capacitance? Obviously, we know from basic diode theory that the depletion layer width will increase. So C is epsilon A by D. So capacitance will decrease. So that is what is mentioned here. Okay. So by changing the reverse bias voltage, you are getting a change in capacitance. So that's why it is called as a varactor diode. Okay. So this is the equivalent circuit. So you see L and C are in parallel. Sorry, this L and C are in parallel. So that is why it is a resonant circuit. So then we have p-ion diode. So as I told, pulse indicates very high doping. So P plus I and N. I is what? Intrinsic semiconductor material. So it is a pure material with very minimum or no doping at all. And P plus will have electrons as majority carriers and N plus with holes as minority carriers. Sorry, holes as majority carriers. Right? So whatever I said, you can show with the help of this graph. So high resistivity is this where there is no doping, and if you are having very high doping, it is a low resistivity region. Okay. So and this is the ideal case, but practically what will happen is it will be like this. Okay. So then you have pi type PIN diode. So it has heavily doped PN in regions but separated by lightly doped P type intrinsic layer. But if it is separated by N type intrinsic layer, it is a V type PIN diode. Okay, and the thickness is usually 10 to 200 micrometers. So remember, it is micrometers. So obviously these diodes are very small because they are used at microwave frequencies, right? So lambda is C by F. So frequency is high, so the wavelength should be very low. So that is why the length, the length of the or the size of the device is very low. Okay. So next, so essentially it does not operate at all in reverse bias. So what happens in forward bias is the electrons are injected into the I layer. So electrons from the N-type layer are injected into this I layer, and holes are injected from here. So because of this, what happens? This layer decreases. The width of this layer decreases. So what happens? The resistivity decreases, right? So it was a high resistivity. So electrons and holes are there. So resistivity decreases and current starts to flow, right? So the low resistance is offered, that is resistivity decreases in the forward direction, right? So this is a very important point. When the bias is varied on the PIN diodes, its junction resistance changes from a typical value of 6 kilo ohms when it is reverse biased to around 5 ohms when it is forward biased. So this gives a hint that it can be used as a switch. So again we have taken the example of what, coaxial line, right? So then this is the equivalent circuit. So it can be used as a switch, SPDT, single pole, double throw, phase shifter and amplitude modulator. Then we went to tunnel diode invented by Isaki, right? So what it is essentially a PN junction with an extremely heavy doping on both sides of the junction and an abrupt transition from P side to N side, right? So what happens, it exhibits a negative resistance region. So that is when you increase the voltage, the current decreases. So that is not following Ohm's law exactly, right? So then I have explained this diagram 2-3 times now, so I will not explain. So whatever is written here is just the explanation of this diagram, right? So just write what is happening in this graph, okay? And this is the symbol of tunnel diode. So what happens when it is unbiased? The Fermi levels are at the equal level, so there is no transfer of energy, right? So there is no tunneling here. So essentially the net tunneling on the thin barrier is zero. But as you increase the voltage bias from 0 to Vp, where Vp is the peak voltage, so what happens is, this is the conduction band. So since the voltage has increased, this creeps into the field state, okay? So that is shown by the dark color here. So since electrons are present here, they can go to this empty state which was over here. So tunneling can happen here. So due to this tunneling, the forward current will increase as bias voltage increases. So as you increase the voltage to a point Vp, so this completely will get filled. So all these electrons can go here. So that is the peak voltage. But what will happen if you further increase above Vp? This will go above, right? So the current will start to decrease because the number of electrons going here will decrease, so current will decrease. So even though you are increasing the voltage, the current decreases. So we say it is a negative resistance region, right? So if you further increase, there will be nothing to go, right? That is what is shown here. So then the applications. So then we went to gun diode. So gun diode is a transferred electron device. So it is a bulk semiconductor device, especially uses what, gallium arsenide. Okay. So then we saw some differences that TEDs are used with hot electrons and transistors with warm electrons. So then we saw gun effect. So by gun effect is basically the observance of negative resistance. So gun observed that above some critical voltage, which is a very high voltage of the order of 2 to 4 kilovolts per centimeter, the current in the specimen becomes a fluctuating function of time. So even though you are giving a DC, diodes essentially work at DC, right? So what you are observing, as time as above some critical voltage, the current becomes a function of time. Okay, even though you have given a DC input. So then we have RWS theory, Ridley, Watkins, Hilsum theory, so or two valley theory. So we have a lower valley where we have a lower effective mass and a higher mobility. Then we have a upper valley and where the mass is high. So since the mass is high, the velocity will be low, and there is a band separation of 0.36 electron volts. So what we essentially require is, so essentially the working of gun diode is the transfer of electrons from this lower value to upper value. So for that what we apply is the electric field. So when the electric field is less than the lower value electric field, all the electrons will be here, right? So the electrons occupy states in the lower value, right? So since here there is a high mass, so the average velocity will be, sorry, there will be low mass here, so the velocity will be very high. So this leads to high current density, obviously, because the velocity is high, and hence the positive potential difference resistance or the ohmic region. So as you increase the voltage further, so some electrons can go over to the upper value, right? So because of this, the velocity starts decreasing here, right? So the current density also starts decreasing. So as you further increase above the upper valley electric field, all the electrons can be seen here, right? So what happens? So the current density further decreases. So because of this, what happens, you can see, since the current is decreasing even though the electric field is increasing, so negative resistance is exhibited. So we can say the gun diode is exhibiting oscillations now, right? So then domain formation is what? So when we are in the negative resistance region, a very high electric field is generated, so that is called as domain. So based on this, and the material properties and operating conditions, we have four modes: gun oscillation mode, stable amplification mode, LSA oscillation mode, bias circuit oscillation mode. So these are classified on the basis of material parameters and the frequency length multiplication and doping multiplied by length, right? So we said that gun oscillation mode is unstable, so it is not used, so we go for stable amplification mode, right? So then we have under stable amplification mode transit time gun domain mode. So again FL is 10 raised to 7, but here tau naught is equal to tau t. So tau t is transit time of electrons and tau naught is period of oscillation. So because of this, the efficiency is very low, order of 10% only. So we increase the electric field. So what happens? Tau naught is greater than tau t, right? So current is seen towards the anode also, right? So because of this, the efficiency increases. Then finally we have quench domain mode where tau naught is made less than tau t, so current is not able to reach the anode. So because of this, the efficiency decreases. So then we went to yesterday avalanche transit time devices, right? So they rely on the effect of voltage breakdown. So I explained what is voltage breakdown with the help of coaxial cable. So you have a conductor, two conductors separated by a dielectric, and it is a circular wave, circular geometry. So if the voltage between the two lines goes above 3 into 10 raised to 6 volts per meter, volts per centimeter, means in a span of 1 centimeter, if the voltage is above 3 megavolts, the dielectric breaks down and we have the breakdown effect. So that is what is used. So that is a problem, but it is used as an advantage in the avalanche transit time devices. So this breakdown word gives a hint that why it is called as avalanche. So let's see why it is called as avalanche. So first is what? Impact diode. So it is impact avalanche transit time diode, used from 3 to 100 gigahertz, and it can be used at very high powers. So this is the structure: P plus N N plus, or P plus P N N plus, or P plus I N plus. And you see the doping is very high here. So resistivity is low and the resistivity would be high, very high here, because the doping is low here. So this plus indicates very high doping region. So usually we use GAS again because it provides the highest efficiency for the construction of this diode, semiconductor materials which we use. So now we said that negative resistance should be, we again want oscillations to be sustained. So negative resistance region for DC we saw that they help in sustaining the oscillation. So same way we can say that negative resistance is there for AC also if it exhibits for DC. Okay, and we redefine negative resistance as, we saw that V equal to minus IR for a negative resistance, that is if voltage increases current decreases. But if we say, if we are able to prove that voltage and current are out of phase by 180 degree, then also we can say that negative resistance is exhibited. So this is the structure. So we are giving a reverse bias of more than 400 kilovolts per centimeter, so that this P plus N junction breaks down. Okay, so what happens because of that? Such a high potential gradient reverse biasing the diode causes a flow of minority carriers across the junction. So what are the minority carriers for P plus? Electrons. That's why minus is shown. So this bounce over to the N region. Okay, so if now let's say the oscillations are existing. Okay, so how will the oscillation, first oscillation will be produced? So if you switch on this DC source, some noise will be there. So due to that noise, some RF oscillations will be generated. So our job is to sustain those oscillations. So what happens is, because of the breakdown, the electrons and hole velocity is very high. So because of this very high velocity, the GAS crystal, so essentially from the GAS crystal, these electrons and holes are knocked down. So continuously these are knocked down from the structure. So continuously electrons and holes are generated at a high rate. So this is called as impact ionization. So these additional carriers, which are electrons and holes, continue the process at the junction, and it now snowballs into an avalanche because continuously electrons and holes are generated. So this effect is called as avalanche. Okay, so if you see the figure, this process takes a time such that the current pulse maximum, so this current pulse maximum and this voltage maximum are out of phase by 190 degree. So further 90 degree is required for 180 degree phase shift. So that is achieved, that since the current is going to travel towards the anode, so it is going to further travel here. right? So because of the reverse bias, the current pulse moves towards the cathode at the drift velocity dependent on the presence of high DC field. So we can adjust the time and the thickness of the highly doped N plus layer so that the current travels with a phase shift of 90-degree here between the voltage 0 and the negative voltage maximum. So if we are able to achieve this with the adjustment of this thickness, then we'll have a 180-degree phase shift, and we can say that the negative resistance has been proved to exist, and therefore oscillations are sustained. Okay, so this is essentially the operation of impaired diode. Okay, so this is the again the equivalent circuit. So then we saw advantages: higher operating range up to gigahertz, right? And about 20 gigahertz, it gives a continuous wave power, means the power does not reduce to zero, for example. Then problems are it is tuning is difficult and relatively high voltage is required because essentially we are operating at breakdown voltages. So it is used in TV transmitter of TV system, then FDM, TDM, and for measurement purposes. So next is trapped diode. Abbreviate full form is trapped plasma avalanche triggered transit. So just a minute, is the recording happening? Yeah. Yeah. So this operation we saw yesterday. So what we use is we place the diode in a resonant cavity, right? So what will the cavity do? Due to the presence of noise generated from the DC source of the trapet, RF oscillations will be generated. So corresponding to the RF oscillations of the corresponding to the RF oscillations, the resonant frequency will be resonating at a particular frequency. So it will take the RF oscillations and resonate at that frequency. So now our job is to sustain that oscillations. So when the RF oscillations begin, they build up extremely rapidly due to what the resonant structure, because it resonates only at a particular frequency. So this increases the voltage much above the avalanche threshold. So because of this, what happens? Plasma is generated. So whenever there is a very high voltage and breakdown, plasma are generated. So the generation of conducting plasma and holes of electrons, which rapidly fill the entire drift zone. But because of this, what happens? The voltage drastically starts reducing. So since the voltage drastically starts reducing, the plasma cannot escape because plasma requires high voltage. So essentially, it is called as uh, plasma is getting trapped, and that's why the name trapped. Okay, so the charge carriers are said to be trapped, and hence the name trapped plasma. So because of this, the relative drift velocity is very low. Okay, so what happens? So since the velocity is low, as they reach the device electrode, they constitute a large current. So when the entire plasma is extracted, the voltage again rises above the avalanche threshold and another cycle is initiated. So this continues further and the oscillations are sustained. So then we saw the advantages, disadvantages and applications. So they are used in radars and oscillators. So next is parametric amplifiers. So we usually get a question, explain negative resistance parametric amplifier and relationship between signal frequency, pump frequency and idler frequency. So, so you have studied a super heterodyne receiver, right? So what it has? It has a radio frequency signal, a mixer, and a local oscillator. So in a super heterodyne receiver, RF signal may be mixed with a signal from local oscillator to generate the sum and difference frequencies. So in the same way, in a parametric amplifier, what happens is local oscillator is replaced by a pumping generator, which is shown here. For example, a reflex klystron. So it is generating oscillations continuously. And the non-linear element is replaced by time varying capacitor like a varactor diode. So this is the varactor diode. So what we want to amplify is this signal frequency to a high high amplitude signal. So where the extra power comes from, the reflex klystron is generating sustained oscillations. So from that we'll get the extra power. Okay. So let's see how this works. So the output or idler frequency F naught in the idler circuit, which is the idler circuit, this circuit. In the idler circuit is expressed as the sum and difference frequencies of the signal frequency and the pump frequency. So since this is compared with heterodyne receiver, so this F naught will be what? Sum and difference of this frequency, obviously, right? So F naught is MFP plus or minus NFS. So when M and N are positive integers from 0 to infinity. So if F naught is greater than Fs, the device is called parametric up converter, else it is called as parametric down converter. So next is negative resistance parametric amplifier. So if a significant portion of power flows only at the signal frequency, means if we are giving significant percent of power flows in only in the signal frequency, pump frequency and idler frequency, all the three frequencies, what happens is a regenerative condition with the possibility of oscillation at both the signal frequency and idler frequency will occur. Okay, so the idler frequency is defined as the difference between pump frequency and signal frequency. So Fi is Fs minus Fp. So when the mode operates below the oscillation threshold, what happens? The device exhibits a negative resistance parametric amplifier. Okay. So this is essentially what you can write for parametric amplifier. So mainly I have used the book Samuel Loyo for all these PPTs, and some part is also taken from this book by Vinit Chauhan. Okay. So only one topic, which is transistors, is remaining in this module. So mainly that will be a guest lecture, most probably. I'll try to have that as a guest lecture. So, and I'll try to not keep it as a live lecture, so I'll try to keep it as a YouTube upload only. So let's see how it pans out. So for today we'll stop here.